Thank you for joining us. It's a pleasure to see such a strong attendance, over 100 participants. Brendan Smith is our presenter today. He's from the group of Professor Jeff Grossman. And it turns out that the group of Grossman's lab has been significantly in the business of figuring out how to make extremely good filtration systems down on the nanoscale. Assisting both in fabrication and simply the phenomena that happen in nanoscale to come up with an amazing filtration mechanisms. So rather than me describe it, I would ask Brendan to take over. As before, if you attended our seminars, hold your questions to the very end. At that point, you can either, using the chat system, write them down or raise your hand and I will call upon you. You also helps if you turn off your videos. That speeds up the connection for the rest of the participants. Please do enjoy Brendan's talk. Brendan, please take over.
Thank you very much, Professor Bolovich, for the kind introduction. And also thank you to Charisse for helping organize the talk. I really appreciate the invite. It's great to be here with all of you. I'm going to switch to share screen now. So I think we have that sort of figured out. Let's see. Okay, so I'm on my screen. Let me know if there's any issues before I continue. Okay, so basically, it was already mentioned by Professor Bolovich, but my name is Brendan Smith. I'm a current postdoc working with Jeffrey Grossman in the Material Science and Engineering Department here at MIT. I also did my PhD in the same group. I just had so much fun during the PhD that I came back to work with Jeff for the postdoc also. And really, we've been quite focused on the goal that I want to present today, which is over the last 5 years or 6 years, commercializing a new type of nanofiltration technology. And the choice of words in the title there, pressure, concentration, and rejection. For those of you who are familiar with the membrane filtration space, those are clearly three very important metrics and parameters in membrane filtration, but they're also things that we all experience, as graduate students doing research, as postdocs, and also as entrepreneurs. And so I thought those were kind of three words that could kind of tie us all together here on the call today. And it's exactly those kind of worlds that I want to speak to. I think I want to talk about not only the technical development from the fundamental stage to scaling up and ultimately, hopefully, the commercial stage, but also the entrepreneurial journey of someone with a technical background trying to commercialize new technologies with the hope of having an impact in the world. And so hopefully there's, along that parallel storyline, something that's interesting for everyone here on the call. And I welcome any discussion or questions we can have after the talk and, into the future as well. Happy to connect with people after the call offline as well. And so just a brief background, really motivation, as to why we actually do what we've been doing for the last 5 or 6 years. And this all really started with kind of taking a close look at energy efficiency, wasting of water, globally in our mega industries today. And really taking a closer look at why that happens and what maybe we could do about it to improve the situation. And so I think we're all aware here on the call that a lot of industries globally today are pretty inefficient. And there's a couple of examples. I would cite textiles, maybe one that's a bit lesser known. We actually consume about 8 trillion liters of water globally per year in the textile space. Oil and gas, probably something people are a little bit more familiar with. About 1 trillion liters of water per year here in the US is consumed, mainly via hydraulic fracturing and other extraction techniques as well. And then in terms of energy in the chemical production industry and petrochemicals and elsewhere, we consume upwards of 100 terawatt hours of energy per year in that space. And so to really think about how we could start to lessen this impact, we have to look a little bit closer and see where most of this waste or consumption really occurs. And it turns out about 10% of global energy use can actually be attributed to a specific part of industrial energy use, which is industrial separations. And industrial separations is really just a broad kind of catch-all term for taking these complex mixtures, be they in liquid or gaseous form, and separating them into their different components, either in terms of the waste stream or in terms of the process stream to produce some kind of product or good. And when we look even closer, it turns out about 80% of all industrial separations globally are done using thermal methods. So things like thermal distillation, which a lot of us are probably familiar with, whereby really we're only taking a complex mixture and essentially lighting it on fire and boiling off different components at different temperatures and pressures, and then recondensing them or letting them escape into the environment to basically rid ourselves of these waste products. And this works pretty well. It's been around for over 100 years in some way, shape, or form. But it's extremely energy inefficient. And this is really based on the lack of ability to reclaim thermal energy and prevent it from going just out into the environment, essentially becoming waste energy. And so there are alternative methods, and the one we want to focus on today is membrane filtration, which can actually be about 10 times more efficient and can accomplish in many cases the same goal. And so the question that probably prompts in your mind is, well, if we can accomplish the same goal for 10 times less energy use, why aren't we doing that today? And so then we kind of pivot to look at membrane filtration landscape and really start to think about, why is it that we're not actually using these technologies? And so this is a pretty simplistic look at the landscape. I tend to think about it in terms of durability on the y-axis and filtration performance on the x. Of course, durability can mean a lot of different things. When we're talking about filtration performance, there's really two main metrics here. One is the selectivity. So can we remove or separate the species of interest from the feed stream into the permeate and concentrate streams of that membrane filtration technology? And then the second is really the flux or the permeability. How much solution, be it water or organic solvent, for instance, or a nitrogen oxygen mixture can be passed through a membrane per amount of energy or pressure that you're applying to that feed stream. And so, one we're probably already familiar with in terms of different buckets of membrane technologies is polymeric membranes. And so these have been around for about 80 years with a lot of incremental innovation over many decades. They're relatively cheap and scalable and extremely tunable. And so we can see excellent selectivity in polymeric membranes anywhere from desalination, where we're selecting out monovalent ions, all the way up to, say, pulp in orange juice, where we're taking out microscale or millimeter scale solutes out of solution or suspension. And so polymers have excellent performance in this regard, but where they really fall short in a lot of industrial environments that are much harsher chemically and thermally is in their fragility. And so we see these membranes melting, degrading, and dissolving under acidic or basic conditions, high temperatures, and mechanically intensive abrasive conditions as well. And so what you can do is actually get around this challenge excuse me, by going to the ceramic membrane technologies. So these are your silicon carbides, your titania, your zirconia, your really tough, hard, strong, durable materials. And while these offer ultra high durability, they're actually not so great in terms of nanoscale selectivity. And so things as small as small molecules in pharmaceuticals, short chain hydrocarbons, and heavy metals, for instance, actually typically can't be removed via ceramic membrane filtration. What's more, they're also pretty expensive from a capital cost perspective. And so you see here, almost 100 times more expensive in terms of capital cost than your average polymer membrane. But really, it's not quite the full picture. You really want to think about it in terms of the ultimate lifetime cost to the end user. And so ceramics are advantageous in that you can actually perform much less maintenance. They have a much longer lifetime, maybe 2 to 5 times longer in terms of years of use before replacement. And so it ultimately can become sort of equal in terms of lifetime cost to the end user between ceramics and polymers. But there is that barrier to the initial capital cost in many cases. So it's important to keep that in mind. And so just a brief comment on sort of the picture of innovation, how we think about doing that. Now that we've identified this upper right-hand corner gap in this technology landscape, I think this is a pretty cheesy and common way to represent, quote unquote, the correct way to innovate. And I think in an ideal world, we would identify an issue, a nail that we have to drive into a piece of wood. We would completely understand to the fullest extent, everything about this challenge and this need that's required to be met. And then we would go out and design a perfect solution to meet that need in every way, shape, and form. And I think this is almost something that almost never happens in its entirety, and it really represents one end of the spectrum in really a perfect world. On the other side of the spectrum, we have the quote unquote complete wrong way to innovate. And that's, I think, in the entrepreneurial community, a way that people actually prescribe to academics, like a lot of us, in terms of how we actually try to bring a technology to market, in that we totally blindly invent some kind of technology or some kind of product, and then we go out searching for an application that we could apply this product to. I think this is almost always never done as well. I mean, very few of us on the academic side are blindly going out and creating random technologies to which we're not sure if there's an application or not. And I do want to mention here that, of course, there's a lot of academic research that doesn't seek to be applied in the broader world immediately. It's more based on understandings of phenomenon or scientific concepts. And that's obviously extremely valuable as well. But today, based on my experience, I want to talk a bit more about the the technologies or solutions that we're trying to apply rapidly to the world or to industry or society at large. And so I think, to this point, what's most common on the academic innovation scene is really, us as academics have sort of in mind a concept or a problem that needs solving. We have sort of a vague idea about it. We've read a few papers on it, maybe a few reviews, and we have a rough sense of what features we might need to design in order to improve the situation, societally, environmentally, or what have you. And so we go out and we design some kind of flashy, new, extremely innovative solution, maybe one that's quite expensive. And then when we finally pivot our attention to how to actually implement this solution out in the world, what we see is that it's actually not perfectly suited for any existing issue, but rather there are this whole complex landscape of issues that are present, and we're not really sure how to correctly navigate this, how to understand the issues, and to apply our brand new shiny hammer to one of these problems that really needs fixing. I think some of the issues that are typically, I wouldn't say ignored, but often overlooked at that early stage of conceptualization and planning out our research and designing the product that we're going to actually build is a really thorough kind of investigation of what are these existing solutions. Are there things which already work pretty well, which could be tweaked slightly to achieve these goals? Are there things that I'm not even aware of that can accomplish a similar result that can be pivoted from another industry, for instance, or application? Another one is price point. So often we design these excellent solutions that fulfill all the needs, if we're lucky, that are required by industry or some other application. But the price point might be 10 or 1,000 times higher, and there might be no way to actually bring that down to something that's economically feasible. And I think it's okay, obviously at first to have much higher price point to your technology or solution. There has to be a path forward in order to actually, drastically reduce the cost of manufacturing that solution, be it economies of scale or switching of your feedstock or making your process much more lean, for instance, or going to a roll-to-roll process over a batch process. So these are all considerations that we should be thinking about. And then the final interesting piece is, are you designing value in your technology, or are you designing features? And features are really a list of specifications that your technology can provide. But value is really how the customer is going to use those features to extract value, either economically, environmentally, or societally, for instance. So just a quick plug before we jump into kind of an example in the shape and form of what we're doing in the Grossman lab. One program I'd recommend to anyone who's even thinking about trying to commercialize some academic technology is the NSF Core Program. We actually did this about a year ago, and I would say it was probably 2 years too late. This program essentially goes through the whole process of figuring out what's the landscape, what are the pain points, and are you providing a value or features through your technology? And so anyone who's thinking about even beginning to come up with an early stage technology that might be commercialized one day, I would highly recommend this program, and happy to talk about it, afterwards if you want to reach out to me. So back to what we're doing. So we did identify this gap in the upper right-hand corner of that plot I showed previously. And so our goal then became, how can we take a material that's intrinsically durable in order to fulfill that y-axis requirement of the landscape, and then poke small holes in it essentially to fulfill the filtration performance requirement? And can we do this at sufficient resolution and with sufficient control to go down to, say, the nanofiltration landscape, where we can access these small molecules, divalent salts, heavy metals, etc. So what we did come across was this approach called metal-assisted chemical etching, which was invented about 15 years ago, somewhat by accident. It essentially involves a technique of punching small pores, or actually any size feature, into a silicon substrate. And so just for an overview, so we all understand where we're coming from, you essentially would start with a crystalline silicon substrate, as shown on the slide. You would deposit some kind of noble metal feature on that surface, be it silver, gold, platinum, palladium. They all work fairly well in different ways. And then immerse this in a chemical solution containing hydrofluoric acid and peroxide, which are both pretty common chemicals in the semiconductor space. So the net effect here is that you get a passive electrochemical process where you're reducing the peroxide at the surface of your noble metal. And this then injects that hole into the silicon, thereby oxidizing it very locally at that interface between the metal and the silicon surface. And that oxide is then subsequently almost immediately consumed by the hydrofluoric acid in solution. So what this does is it eventually forms this little pit on the nanoscale, or essentially the scale of your catalyst particle, that can then continue on to form eventually a very high aspect ratio nanopore as this this catalyst particle or feature continues to sink deeper and etch deeper into the silicon wafer in this case. So that's just a very broad overview of the technique. And then most of our innovation, I should say, over the last 4 years has been really innovating around the catalyst deposition and form factor of that catalyst to make it as small as possible, as dense as possible on the silicon surface, and then allow it to sink as deeply as possible, preferably through a thick silicon slab that can then act as our membrane filter. So just so you have an idea of what this looks like, these are a couple of TEM images where on the left side we have silver catalyst particles deposited on a very thin silicon film, in this case only a couple hundred nanometers of thickness. And on the right side, this is following that metal-assisted chemical etching approach, where on the left, the dark contrast is actually the metal catalyst. And on the right side, the light catalyst, the light contrast features are actually the holes or pores that are punched through that silicon film. And I do apologize, the scale's a bit mismatched here, but you can get an idea of how the size of the particle actually translates pretty closely to the size of the pore in that silicon film. So really the bulk of our innovation was around sort of minimizing the complexity, minimizing the cost of this process. And eventually we were able to take it down to about 2 steps using only common and scalable tools that are available at scale in industry today. And so again, the first step is that catalyst deposition. We currently use a sputtering approach to deposit that metal on the silicon tile. And the second and final step is that chemical etching step. Really 2 main advantages, compared to the status quo techniques available today in industry, things like electron beam lithography followed by reactive ion etching, for instance, are that we can obtain much smaller pore diameters relative to these more controlled microelectronics type approaches. And again, we don't really care about where these features are placed, only that they're highly dense and are relatively homogeneous in terms of pore size and aspect ratio. And that being said, the second advantage here is that we can obtain much higher aspect ratios in these nanopores than you could with, say, an IRE approach, where we can get aspect ratios over 2,000 to 1, allowing these very narrow nanopores to penetrate through a very thick silicon wafer, which then becomes our membrane. And so the other important piece here is that we were able to scale up. And so obviously when we started this process, we started working on a very small scale, in this case back in 2015 on a TEM grid, for instance. And we can see here that we were indeed able to confirm the very first question was, can we make these very small pores in this intrinsically chemically and thermally durable material? And so we found out back in 2015 that we could do this, at least on the very small scale, and then started to scale this up to something that could actually look like a membrane product in the near future. So we went to the chip scale in 2016, and then moved to our first kind of functional membrane type of morphology and these disc filters. And for those of you who are in the microelectronics space, you'll recognize this as a silicon wafer that's been treated to be initially thinned and then chemically etched through using the process that we developed. And then the final piece of this journey to date has been the move to this, what we call tile filter. And this is, looks a bit different. This is a common photovoltaic silicon wafer that we can buy off the shelf in bulk for $3 or less per unit. And this allows us per area to be over 100 times cheaper than what we can get with that circular disc filter in 2018. So this is moving us closer and closer to being able to build this at scale for a price that's economically feasible. When you zoom in on this, just to get an idea of the morphology itself, you can see, we saw that TEM view of the single pore. In this case, we can see these pores scattered across the surface. They do look a little bit larger in these dark contrast areas. That's because we have sort of a cylindrical or funnel-like shape, more so than cylindrical, more of a funnel-like shape at the surface down into the bulk of the silicon, where these pores contract quite steeply to around that 10 to 5 nanometer range. So looking in the cross section, if we were to cut this wafer in half and look at the cross section in SEM to give you a bit better an idea of the morphology, we can see at the very top of the slide here the initial chemical etching surface where we initially deposit that catalyst. And then these long dark contrast lines are representing the nanopores or channels themselves, which run from top to bottom of the membrane. And that really allows the solvent, be it water or some other organic material, to be forced through the membrane under pressure, while the diameter and chemical character of those pores is actually dictating what can and can't pass through the membrane. Chiefly that's occurring at the surface, ideally at those pore entries. So what we are able to do is actually modify the pore diameter. And so this gives us a tunable performance in terms of what we can reject from solution, not only in terms of the pore diameter, but also in terms of hydrophilic and hydrophobic interactions, as well as other chemical interactions. And so this has kind of bestowed with this technology, the opportunity to have a platform technology where we could target different applications depending on the needs we see in industry today. So just a bit on the actual filtration testing. The way we do this is pretty simple. We're able to mobilize these membranes in these pressure cells that we can buy off the shelf. In the bottom of this cell here, as you can see, the test solution is then placed in that pressure cell chamber above the membrane itself. Pressure is applied in dead-end configuration via compressed gas, and we're able to squeeze the water or other organic solution through the membrane and out through that spout where we can analyze it in real time. And so a couple of different experiments we've performed. We've done a lot of work with organic dye molecules and aqueous solutions. These are really easy to characterize and also monodisperse in terms of their hydrogenated side or hydrodynamic radius, for instance. The smallest thing we've done is with arsenate, and that's obviously a big problem in places like Southeast Asia in terms of the groundwater contamination. About 100 million people suffering there from exposure to arsenic currently. And so we're able to remove that upwards of about 99% from the feed stream. And this is working ourselves down towards divalent salt type of rejection. Also important, not only the size of what you're rejecting, but also the chemical character. So one major issue with polymeric membranes, specifically with oil-water emulsions, which are quite common industrially in a lot of different spaces, is that the oil readily fouls the polymer membrane surface and then blocks the flux of water relatively quickly across that membrane. And so what you'd really like to do is be able to do this without any kind of fouling or minimal fouling, or at least cleanability once you do get that fouling occurring. And so what we have done is done a lot of different cleaning studies with the membrane. We've used these really heavily loaded oil-water emulsions, as you can see in the top right. Basically sucked all the water out of this solution to leave the solid concentrate. You can again see on the very far right side. And then we've done this sort of in cycles where we've performed the experiment, cleaned the membrane, put it back in, duplicate the experiment once again, and then performed a different cleaning step. And so we can see that, through different cleanings, be it with piranha solution, which is concentrated sulfuric acid and hydroxide, or hydrogen peroxide rather, or organic solvents, or thermal cleaning, we can rejuvenate the flux and permeability of that membrane back to the initial value. And so another important point, obviously, is the cost. And so we really need to get an idea of the lifetime cost to the user to really be able to make direct comparisons. However, what we can do is actually compare to current closest competitors in terms of what ceramics are on the market today. Membranes that would offer similar durability in terms of chemical and thermal durability, but maybe be a little bit more expensive. And so we actually have purchased some of these. This is our closest ceramic competitor. You can purchase a similar surface area in this long tube at the top of the slide for about $320 per unit. And we think we can make our silicon at scale for less than $5 per unit. So there's obviously a markup involved in all these products, but this makes us feel relatively confident that we can indeed be quite cost competitive. So looking back, at this plot, we know that, or we think at least that we have both durability and filtration performance required to start to think about filling this gap. The question then becomes, out of the tens or even hundreds of different applications across many global industries, what's our best target application in terms of where we can provide the most value? And so, I know I'm getting a little bit short on time, so I won't spend too much time through this section. But just to provide sort of an example of our thinking on this and how we identify potential markets and applications, I think you really need to start with a spec sheet by kind of speccing out everything you think your technology can do in terms of what's the most important in your target industry. But that's not the final answer. What you then have to do is go talk to the people and stakeholders in these industries and hear their feedback without biasing it as much as possible, and really then get a sense of, are your estimated or hypothesized specs actually important, or are they things that you just thought were important? And so really the takeaway message here, and something that's drilled in through the NSF Core as well, is to really talk to those stakeholders throughout this process. So an example for us, and I'll probably finish up here in a few more minutes, is in the textiles effluent treatment space. And so we did see a need, as I mentioned at the outset, over in southern India, for instance, about 4 trillion liters of effluent are produced annually. And 80% of that is actually not treated at all and simply dumped into the surface or ground or river water. So clearly a very difficult situation there. There's also, though, an adoption incentive from the perspective of these textile mill operators, in that an average mill might spend upwards of $2 million per year just on the effluent treatment if they're doing it correctly. And that kind of equates to a market size of around $3 billion when looking at that whole kind of sub-market in the southern Indian geography. So just a rundown of sort of the general way in which this process is done. This is sort of a 12+ step process, but I've sort of boiled it down into the 6 most important stages here in terms of operating and capital cost. So things like active cooling, electrochemical degradation, and here you have 2 different filtration steps, which are both currently performed with polymeric membranes, which are far from adequate in terms of offering multiple year, 5-10 year lifetime and low cost operational costs. They're quite high maintenance in terms of cleaning and replacement cycles. And this all kind of boils down to the final stage, which is distillation, which today actually accounts for about 20% of the total effluent volume, which is being treated in that manner, mostly based on the inability of those coarse and fine polymeric membranes to really handle higher concentrated effluent sludge, which is created when you pull out more water from that mixture through the membranes. So what we think we could do in concert with talking to a lot of these operators and partners over there in India is actually erase a lot of these stages, namely active cooling, because our membranes can tolerate much higher temperatures, and then fold in the coarse and fine filtration into a silicon membrane stage. What this would do is actually ultimately reduce the distillation volume requirement from about 20% of the total volume down to about 2 or 3% of the total volume, if not eliminating it altogether. And so starting from that point, we can actually do a lot of techno-economic modeling, and really validating this again with these partners is extremely important. And so what we come out with in terms of an estimate, and of course a very rough estimate until we can actually do some on-site piloting, which is hopefully in the cards within the next year, is a CapEx which is relatively similar, but even a little bit less, about 75% of the total for silicon filtration as opposed to the status quo today. But even more importantly, as I spoke to before, is the operating cost. And so we estimate about a 60% savings in OpEx annually for these producers if they were to fully switch over to the silicon membrane nanofiltration scheme, as opposed to the one I showed that's kind of the status quo today. So finishing up, just to really frame the value proposition instead of the features in this case, it's really a 60% OpEx reduction to those end users. And this is me on the left, smelling some really nasty textile wastewater. And then, that really equates to about a 2-year payback period in terms of the initial upfront capital cost of the system. And in terms of the benefit for society and for the environment, about 1 trillion liters of water saved per year that we can actually recycle back into the textile dyeing process, as opposed to boiling it off into the environment through thermal distillation. And so I'll wrap up with that. I hope that was interesting and useful to people. I'm more than happy to take questions, of course. I think as a takeaway, I just wanted to instill in everyone here that there are, of course, numerous opportunities and a lot of resources that I haven't touched on for translating a very early stage academic research into near-term impact in the near future for us, hopefully. And I also want to emphasize as a second point that it's really important to keep in very close contact with the stakeholders. Don't make too many assumptions without validating them at a very early stage, or you might pay for that later in the process with time and money. And yeah, I just hope that everyone took something away from the talk. So thank you very much. I'd like to thank our sponsors listed on the screen here, and please feel free to reach out to me, offline as well at my email listed on the top right there if you have further questions later on. But for now, I'll stop sharing and we can address any questions.
Brendan, thank you very, very much. As of course, all of us can do, we can go to the reactions, and I'm gonna choose a reaction. Thank you so much. So if you have any questions for Brendan, please go ahead and type them in the chat. That's one way to do it. The other way to do it is to raise your hand. I will go through as best I can through the 7 screens of participants and identify the ones that might have a question if you raise your hand. Otherwise, the chat will be read first. So there are a few questions already coming through the chat, and so I'm going to start relating them to Brendan. Brendan, this is a question for Vinay Goel. How do you produce large area modules?
Yeah, that's a great question, and one that we've been sort of thinking about from the very early days of choosing silicon and choosing this process as our sort of go-to focus process. In this case, if you contrast this with a polymeric membrane where you can literally do roll-to-roll fabrication of 10 square meters of membrane, clearly there are some challenges with silicon, and most of those are related to the type of feedstock you can acquire. And so you can see that we're acquiring this photovoltaic feedstock. You can get up to wafer sizes of 400 millimeters in diameter. And so clearly very still space or area limited in terms of comparison to polymerics. So what we need to do instead is think about how we can multiplex these individual tiles in a larger module. And so we are pursuing and coming up with different designs where we can mobilize, say, 100 different membrane tiles in a flat sheet and then start to put those in parallel with each other to get, up to, say, 1,000 square meters in a 3 by 3 by 3 meter stack, for instance, on a factory or plant floor. And so there's a lot of engineering design challenges that go along with that, and we're learning a lot in terms of what's already been done, for similar technologies, but it's clearly a challenge that's sort of ongoing for us.
A related question from a couple of attendees is on the fragility of silicon, mechanical stability of these filters. How robust would they be under high pressures?
Yeah, that's another great, very relevant question. And so, of course, if you hold up a silicon wafer just with your hands, you can crack it very easily, especially with the thin silicon that we use. The very important thing, actually, in all membrane filtration is the way you support the membrane, the active membrane layer. And so, even in with polyamide membranes and desalination, they have underlying polymeric support layers, as well as spacers. And then ceramic membranes, you have a much more robust underlying support layer, where ceramics are also very brittle materials that can crack. But to actually answer the question, if you correctly abut the silicon membrane or slab on a support that's robust, you can go over 1,000 psi in terms of the hydrostatic pressure across the membrane, as long as it's correctly supported.
Another related question on clogging. Is that an issue given how small the pores are?
Yeah, so clogging and fouling and scaling are just cake formation, all different ways of just saying we're reducing the flow of solvent across the membrane based on this blockage. And so all very extremely important issue for any membrane technology. And of course, clogging will occur in any membrane technology, not just polymeric ones or ceramic ones. Kind of three things do you think about as a membrane person when you think about reducing that clogging or fouling rate? One is hydrophilicity. And so we strive for a very hydrophilic surface. And as far as I've seen, we have the most hydrophilic surface out there in terms of membrane technologies, contact angle of about 10 degrees or 12 degrees, static contact angle, relative to, say, 20 or 30 for the best ceramic membrane. Second is surface roughness. So if you go for a very smooth surface, which we do have, you can minimize the purchase for these foulants to cling there to the surface. And third is cleanability. And so, once clogging does occur, how easy is it to regenerate that membrane flux with standard cleaning chemicals, protocols, back flushing, aeration, using bubbles, for instance, all different kinds of cleaning approaches. But those three things are really the things that we're concerned about, and which I think we do fairly well in terms of the anti-fouling performance.
In the process of actually making the membranes, have you attempted different metals as catalysts? And what is the catalyst turnover?
Yeah, great question. So in terms of the metals, yeah, those four I mentioned are ones we've looked at, and they all have sort of different characteristics in terms of the etching performance. And we've eventually settled on a combination that works best for us, mostly based on the etching rates. You want that to be fast, and you want it to be relatively uniform in its direction. I don't think I mentioned we take advantage of the crystalline silicon lattice to achieve that directionality from top to bottom of that wafer. And so different metals will give different directionality, different performance in terms of directionality. In terms of the catalyst being reclaimed, you could do that. We haven't done that currently. There are methods you could use to go back into the membrane after production and dissolve out the catalyst particles. But as of yet, we haven't explored that approach.
What is the pressure loss over the 5 nanometer filters? Is it similar to polymer filters?
Yeah, it would be similar. So, we chiefly look at permeability. So for a certain applied pressure, a certain membrane area, a certain amount of time, how much flux you're going to get through that membrane area. And so for a polyamide desalination membrane, you typically see transmembrane pressures of anywhere from 600 to 1,000 psi. And at our pore size down below, approaching 2 nanometers, we would be looking at a similar type of pressure drop across the membrane, where on the permeate side, you're basically at atmospheric pressure.
Have you considered using these membranes in tangential flow mode?
Yeah, definitely. So I did mention, I didn't have time to go too much into this, but I mentioned that we use dead-end filtration for a lot of our testing, which is still true. It's a quick and easy way to evaluate all those important membrane parameters I discussed. Tangential flow is something we're also doing currently. We've done some custom design of modules. In that way of scaling up that I mentioned with a larger, say, 9 cubic meters squared module, it would be all tangential flows. What tangential flow helps with is actually alleviate the fouling concern, because you create this flow across the surface, and you can actually reduce fouling rate if you have a high cross-membrane or transmembrane velocity to that solution.
You mentioned silicon and its crystalline direction helps you in the way of etching the holes. But are there other alternative substrates you would consider?
So far, mostly silicon. The reason for that is, number one, the low cost. So for this etching process to work, there has to be energetic band alignment in the materials such that you get that passive electrochemical process to actually be active. And so you can't just, it has to be a semiconductor, first of all. And so we've also thought about things like gallium arsenide for totally different applications. No one's going to use gallium arsenide water filters. The cost and also the arsenide might be an issue. So yeah, I think for our purposes, in terms of water filtration, silicon is the best candidate. There might be other applications, for instance, in roughening of photovoltaic surfaces, where gallium arsenide might be of interest and actually has been explored in the literature as well.
The actual process of making one of the membranes, how long does it take? What is the...
Yeah, great question. So we're sort of blessed in that we deposit very little material. And so you can see those little droplets of metal on the surface. That only takes around a second to deposit that material. The bigger question there is, can you design a roll-to-roll process whereby you can sputter because you need a little bit of a low-grade vacuum to do that? And so there are ways to go roll-to-roll there that are a little bit more complex, and we're not really using those yet. We're looking to do so in the future. And the etching process is a bit longer. You're looking at probably a couple hours to etch through one of these wafers, depending on the wafer thickness. And there are things you can do involving temperature and applied bias, maybe to decrease that time limitation that we'll also be exploring.
Mm-hmm. I assume the next thing you can imagine doing are things like biasing the top surface of your membrane or such, given the fact that you are using a semiconducting material. So have you considered exploring applications of electrostatic fields for further separation choices you might want to?
Yeah, that's a really interesting question. Something we haven't done too much with the silicon technology, but our group is actually exploring electrified membranes more in the context of, say, carbonaceous materials, because those can also be highly conductive, of course, as most of you know. Definitely something we're interested in exploring further with the silicon as well. It's sort of something that is kind of in the future for us.
Okay. What are the main failure modes of the current silicon membranes?
Mm-hmm. So I think, on the mechanical side, definitely cracking. So physically being brittle obviously can cause cracking if you don't have that correct mechanical support on which to mount the membrane. We're getting better and better at that over time. So we've really designed sort of around that issue at this point. If you're careful, you can really avoid that happening. And the second, I think, is the clogging. And so we're really targeting a few different applications, and textile effluent treatment being one of them, where it's really application specific. And so if you're doing textiles, if you're doing petrochemical production, for instance, those are two very different cleaning modes you have to explore. So we're designing individual cleaning protocols for each application we're targeting to really avoid that long-term clogging and fouling issue.
When you mentioned 5 nanometer pore, you're really talking about size distribution around 5 nanometers, right? So there is some amount of scatter in that size. How does that impact your filtering?
Yeah, so that's a great question. I'm really impressed with all these questions. These are all really great. So ideally, you'd want a completely sharp cutoff. You'd want to have all your pores a single size and nothing above that. In reality, ours are, say, 5 nanometers plus or minus a couple nanometers. So really, and as you probably also know, the larger the pore, you're going to get a pretty exponential increase in flow through larger pores. And so you want to really minimize the amount of pores that are larger than the actual substance you're trying to reject. Then you also have some electrostatic effects and some hydrophilicity effects that can help to mitigate that issue. But that is to say that, yes, we do have some kind of spread around our average pore size, but you want to minimize that as much as possible.
But yeah, I can also imagine you can do a staged filtering where you start with the big pores to get most of the stuff out, and then you can fine polish your final thing through.
Yeah, that's absolutely true. And it all depends on the application. So sometimes you need to have your silicon membrane maybe at a certain stage because it's exposed to a certain harshness of solution, high acidity or organic solvent. And then once you get past that, you can apply a maybe more conventional separation technology, for instance. There are a lot of different configurations. And also to your point, often you have a pretreatment stage with a coarser mesh or coarser membrane. That's much less energy intensive, but you can remove some of those larger things. So that by the time you get to the fine filtration, you're really dealing with the small stuff and avoiding a lot of that fouling that can occur.
Excellent. Brendan, there are a few more questions, but I'm going to stop here. I would very much congratulate you on a fantastic work, both as a journey through your PhD degree, now a postdoc experience that is now springing into the beginning of a startup company. Very much congratulations for that. I will take one more moment and I'll give one more reaction on my end to Brendan's talk. Thank you again a ton. The other thing that I would urge you to do, if you have additional questions for Brendan on this particular talk, you can certainly reach out to him, to Professor Jeffrey Grossman, who's also online, as well as if you cannot find their email addresses, just send them to MIT.nano main email address, and we'll make sure we forward and connect you with any of the questions you might additionally have. Again, thank you very much for joining us today, and I look forward to seeing you next time. Thanks a lot.
Thank you, everyone.